Picture this: a storm-battered ship, its sails torn, its crew clinging to hope as they drift through the endless dark. They're lost, with nothing but the stars to guide them, relying on centuries-old maps and instruments that seem almost primitive by today's standards. But what if I told you that in their struggle to survive, these sailors stumbled onto something far bigger than themselves, something that would rewrite our understanding of the universe itself? This isn't just a tale of survival, it's a story about how human error, desperation, and the sheer chaos of the sea led to one of the most unexpected breakthroughs in science. Because hidden in the wreckage of their journey was a clue, a cosmic breadcrumb that would eventually help reveal the true shape of spacetime. Think about that for a moment. The same tools used to navigate the ocean, the sextant, the compass, the stars themselves, became keys to unlocking Einstein's theory of relativity. It's as if the universe left a trail of clues in the most unlikely of places, waiting for us to piece them together. And that's the incredible twist here. The answers weren't just found in laboratories or telescopes. They were buried in the logs of ship captains, in the drift of lost vessels, in the way the stars seem to shift ever so slightly when viewed from a storm-tossed deck. This is where history and science collide, where the practical struggles of sailors became the foundation for understanding the very fabric of reality. So how did it happen? How did something as ordinary as a shipwreck lead us to revelations about space-time, gravity, and the bending of light itself? That's the journey we're about to take, one that starts with the desperation of lost sailors and ends with the mind-bending truths of modern physics. Along the way, we'll uncover how the stars that guided ships for centuries were also quietly whispering secrets about the universe's hidden structure. And by the end, you'll see the night sky and every voyage across it in a whole new light, because sometimes the biggest discoveries don't come from looking up. They come from getting lost and then finding your way back with a story no one saw coming. During the golden age of exploration, when wooden ships braved uncharted waters, celestial navigation wasn't just a skill, it was the thin line between survival and disaster. Sailors would spend nights squinting through sextants, measuring the angles between the horizon and stars like Polaris, trusting these celestial markers to guide them across featureless oceans. But here's the catch: the more meticulously they recorded their observations, the more they noticed something peculiar. The stars weren't always where they should be. Tiny discrepancies crept into their logs, shifts so slight they could have been brushed off as human error or faulty instruments. Yet these anomalies persisted, whispering secrets no one at the time could decipher. Take the story of Captain James Cook, whose legendary voyages mapped vast stretches of the Pacific. His logs, filled with star sightings and lunar distances, were models of precision. But even Cook's measurements showed inconsistencies, stars appearing slightly out of place when observed from different latitudes or during eclipses. At the time, astronomers blamed atmospheric refraction or imperfections in the sextants themselves. But what if those errors weren't mistakes at all? What if they were glimpses of something far stranger? The bending of light itself as it traveled through the warped fabric of space-time. This is where history takes a thrilling turn. Those same navigational tools designed to keep ships from crashing onto rocky shores became accidental detectors of cosmic truth. When Einstein proposed that massive objects like the sun could bend light, a cornerstone of his theory of general relativity, scientists realized something extraordinary. The star shift sailors had observed for centuries weren't flaws in their methods. They were evidence of spacetime's curvature, with distant starlight bending around the sun's gravity like a ship veering around a hidden whirlpool. Suddenly, the notebooks of long-dead navigators transformed into treasure troves of data, their painstaking records validating predictions Einstein made on paper decades later. It's almost poetic when you think about it. The very tools meant to chart a safe path across the seas ended up mapping the invisible contours of the universe. And it all started with sailors who, in their quest to avoid disaster, became unwitting pioneers of physics. Their struggles against the chaos of the ocean didn't just lead to better maps, they helped reveal the hidden architecture of reality itself. For over 200 years, Isaac Newton's vision of the universe reigned supreme, a clockwork cosmos where space was flat, time was absolute, and celestial bodies moved with mathematical precision. To sailors navigating by the stars, this orderly framework was gospel. The heavens were a fixed tapestry, their constellations as reliable as a lighthouse beam cutting through the night. Armed with Newton's equations, navigators could calculate their position on Earth by measuring angles to the sun and stars, confident that the universe obeyed strict, predictable rules. But beneath this veneer of certainty, something peculiar was happening. The better their instruments became, the more those supposedly fixed stars seemed to wander. At first, these discrepancies were dismissed as minor errors, perhaps a warped sextant lens or a tired sailor's miscalculation. But the anomalies persisted, showing up in logs from ships crossing the equator or observing eclipses. Stars near the sun's position, for instance, appeared subtly displaced, as if pushed aside by some invisible force. Newton's laws couldn't explain it. His universe was a flat grid, where light traveled in straight lines and gravity acted instantaneously across empty space. Yet here was evidence that space itself might be bending, warping under the influence of massive objects in ways Newton never anticipated. This tension between theory and observation came to a head in the early 20th century, when astronomers studying solar eclipses noticed something extraordinary. Stars visible near the darkened sun weren't where Newton's calculations said they should be. Their light had curved around the sun's gravity, tracing the contours of warped spacetime like a ship following unseen currents. Suddenly, those centuries of navigational quirks made sense. The errors in sailors' logs weren't mistakes. They were footprints of a deeper cosmic truth, one that Newton's rigid stage couldn't accommodate. What's fascinating is how long these clues lay hidden in plain sight. Generations of navigators had unknowingly been charting the curvature of spacetime with nothing but sextants and star charts. Their struggles to reconcile theory with reality mirrored the scientific revolution brewing on land, where Einstein was piecing together a new vision of gravity, not as a force acting across space, but as the very bending of space and time itself. The irony is delicious. The tools meant to impose order on the chaos of the sea ended up revealing chaos in the supposed order of the heavens. And it all started with sailors refusing to ignore the tiny cracks in Newton's flawless universe. In 1915, Albert Einstein shattered the astronomical status quo with a theory so radical it rewrote the rules of the cosmos. He proposed that space and time weren't just a static backdrop for the universe, they were a dynamic, malleable fabric, warped and stretched by the presence of mass and energy. Picture a trampoline sagging under the weight of a bowling ball, distorting the path of any marble rolled across its surface. That's gravity in Einstein's universe, not a mysterious force yanking objects together, but the natural curvature of spacetime itself. At first glance, this seemed light, years away from the gritty realities of maritime navigation. Sailors weren't pondering the geometry of the cosmos. they were fighting storms, scurvy, and the ever-present threat of shipwreck. But here's where history played its hand. Those same star charts and sextant readings that kept ships on course held buried evidence for Einstein's theory. Because if spacetime really was curved, then starlight passing near massive objects like the sun wouldn't travel in a straight line. It would bend like a car's headlights appearing to swerve on a hot road. And that meant every time a navigator measured a star's position near the horizon, they might have been unwittingly mapping the very distortions Einstein predicted. The breakthrough came when astronomers realized they could use solar eclipses as cosmic laboratories. During totality, when the moon blotted out the sun's glare, stars usually hidden in its glare became visible. If Einstein was right, their positions would appear subtly shifted, proof that the sun's gravity was bending the fabric of spacetime. And in 1919, during an eclipse off the coast of West Africa, that's exactly what they found. The starlight had curved, matching Einstein's equations to a T. Suddenly, the navigational quirks sailors had grumbled about for centuries weren't just annoyances. They were echoes of a deeper cosmic truth. What's astonishing is how perfectly the tools of the age of sail dovetailed with the birth of modern physics. The sextant, designed to measure angles between stars and horizons, became an accidental detector of spacetime's curvature. The logbooks, filled with frustrated notes about errant stars, were actually recording the universe's hidden architecture. Even the Eclipse's navigators dreaded moments when the sun vanished and celestial reference points scrambled turned out to be the key to validating Einstein's vision. It's as if the universe had been leaving breadcrumbs all along, waiting for someone to connect the dots between the rolling decks of wooden ships and the vast, bending expanse of spacetime. This convergence of seafaring and relativity isn't just a quirky footnote in science history. It's a testament to how the most practical human endeavors, like not crashing your ship into a reef, can unexpectedly illuminate the grandest mysteries. Because sometimes the universe hides its secrets not in ivory towers, but in the salt-stained pages of a captain's log. The year 1919 marked a turning point in our understanding of the universe, all thanks to an astronomer with a telescope and a perfect celestial alignment. Arthur Eddington, armed with Einstein's bold predictions, set out for the remote island of Principe off the coast of Africa. His mission, to capture a solar eclipse, a fleeting moment when the moon's shadow would reveal whether starlight truly bent around the sun, as Einstein's theory claimed. When Eddington's photographs finally developed, the results were undeniable. Stars that should have been hidden behind the sun's glare appeared slightly out of place, their light deflected by the sun's gravitational pull like a marble rolling along a curved track. This was gravitational lensing in action, the first direct proof that spacetime wasn't just a stage, it was a shape-shifting fabric. But here's the twist: Eddington's eclipse wasn't the first time humanity had witnessed this phenomenon. Centuries earlier, sailors squinting through sextants had recorded the same subtle star shifts, scribbling frustrated notes about unaccountable deviations in their navigation logs. Without realizing it, they'd been documenting the curvature of spacetime every time they measured a star's position near the horizon. The difference was context. Where Eddington saw proof of relativity, sailors saw navigational nuisances, tiny errors to compensate for, not cosmic revelations. The parallels are striking. Just as Eddington relied on the eclipse to blot out the sun's glare and reveal displaced stars, sailors often made their clearest observations during twilight or eclipses when the sun's interference was minimized. Their tools, though primitive, were essentially measuring the same distortion. A sextant's precision in capturing star angles made it an accidental spacetime detector. its brass arcs and telescopic sights tracing the same bends in light that Einstein's equations later described. What's truly remarkable is how these two worlds, seafaring and astrophysics, converged. Eddington's expedition, with its meticulous photographic plates and precise calculations, mirrored the discipline of celestial navigation. Both required patience, precision, and a willingness to trust data over dogma, and both, in their own ways, were peeling back layers of cosmic mystery. The irony, while Eddington's work made headlines, those unnamed sailors had been collecting the same evidence for generations, their logs gathering dust in maritime archives. This hidden history reshapes how we see scientific discovery. Breakthroughs aren't always born in labs or observatories. Sometimes they're buried in the mundane struggles of people just trying to do their jobs, whether it's a sailor plotting a course or an astronomer chasing an eclipse. The universe doesn't care who's listening when it whispers its secrets. It just waits for someone to connect the dots between the stars on a sextant and the equations on a blackboard. And in that moment, even the smallest anomaly in a ship's log becomes part of the grandest story ever told. Ship captains of the 18th and 19th centuries kept logs with almost obsessive precision, recording every shift in the wind, every change in the stars. These weren't just journals, they were lifelines, critical for future voyages and the safety of countless crews. But buried in those pages were small, persistent mysteries. Time and again, seasoned navigators would note that certain stars seemed to drift from their expected positions, sometimes by mere arc minutes, a tiny deviation, but enough to throw a ship dangerously off course over long distances. The usual suspects, a warped sextant, a miscalibrated chronometer, or simply fatigue blurring a sailor's vision. Yet even after accounting for every possible error, the discrepancies remained like ghosts in the data. What no one realized then was that these weren't mistakes at all. They were glimpses of the universe's hidden geometry. Take the case of the HMS Beagle, the ship that carried Charles Darwin to the Galapagos. Its logs, filled with celestial observations, later revealed subtle inconsistencies in star positions, especially near the horizon, where starlight had to travel through more of Earth's atmosphere and unknowingly through the planet's gravitational field. Today, we recognize this as gravitational lensing in miniature, the bending of light by mass, warping the apparent position of stars just as Einstein would later predict. But back then, it was chalked up to instrumental error and quietly filed away. The irony is profound. These navigational failures were actually triumphs of observation, capturing relativistic effects centuries before physicists had the language to describe them. The Royal Navy's meticulous record-keeping, meant to ensure safe passage, inadvertently created a treasure trove of spacetime data. When modern researchers revisited those logs, they found patterned stars near the horizon consistently appearing higher than they should, their light bent upward by Earth's gravity. It was as if every ship that ever corrected its course based on flawed star readings had been dancing to the tune of curved spacetime without even knowing it. This raises a tantalizing question. How many other scientific breakthroughs have been hiding in plain sight, disguised as human error? The history of science is littered with examples where anomalies dismissed as noise turned out to be signals. In this case, the noise was the sound of waves against a ship's hull, the scratch of a quill in a logbook, the frustrated sigh of a navigator who couldn't reconcile the stars with his charts. The signal was the universe itself, quietly demonstrating its true shape through the very tools humans built to conquer it. What's even more remarkable is how these maritime records bridge the gap between abstract theory and tangible experience. Einstein's equations might describe spacetime curvature with elegant mathematics, but it's the sextant's brass and the sailor's squint that make it real. Those star shifts weren't just numbers on a page, they were the difference between reaching port or hitting a reef. In the end, the sea, with all its chaos and unpredictability, became an unlikely classroom for relativity, teaching us that sometimes the biggest truths reveal themselves not through perfect precision, but through the stubborn persistence of small, unexplained deviations. While most of us picture astronomers as lone scholars peering through telescopes in remote observatories, some of the most important celestial observations of the 18th and 19th centuries came from an unlikely source: the cramped quarters of naval vessels. These weren't just sailors with a passing interest in the stars. They were trained naval astronomers, officers who combined maritime expertise with cutting-edge astronomical knowledge. Their mission was straightforward: map the heavens with such precision that any ship, anywhere on Earth, could find its way home. Night after night, they recorded star positions, lunar distances, and planetary motions in leather-bound logs, creating mountains of data that would outlive them by centuries. What makes their work so extraordinary is how unwittingly they documented relativistic effects. Take Neville Maskelyne, Britain's astronomer royal in the late 1700s. Tasked with solving the longitude problem that plagued navigation, he compiled exhaustive star catalogues from observations made at sea. His teams noted tiny discrepancies, stars appearing slightly displaced when viewed near the horizon versus higher in the sky. At the time, these were dismissed as atmospheric distortions, but we now recognize them as early evidence of gravitational lensing, the bending of light by Earth's own mass. Maskelyne's meticulous records, meant to perfect celestial navigation, were actually tracing the curvature of local spacetime. The same story played out across navies worldwide. French astronomers like Pierre Méchain, charting stars for the revolutionary metric system, noticed persistent anomalies in their measurements. Russian explorer Fabian Gottlieb von Bellingshausen's Antarctic expedition logs contained peculiar star shifts that baffled contemporary scientists. Even the United States Naval Observatory's early work, intended to standardize timekeeping for ships, inadvertently captured relativistic clues. These weren't isolated incidents. They formed a global pattern of observations that, had anyone connected the dots, might have accelerated Einstein's breakthroughs by decades. What's striking is how these naval astronomers straddled two worlds. By day, they were practical problem solvers, developing techniques to keep ships from running aground. By night, they became unwitting pioneers of fundamental physics, their sextants and telescopes acting as proto-scientific instruments probing spacetime itself. Their dual role highlights a profound truth about discovery. The line between applied science and theoretical revolution is often thinner than we think. The same hands that adjusted a ship's chronometer were, in essence, measuring the universe's hidden architecture. Modern researchers poring over these antique logbooks face a peculiar challenge. The data is their precise angular measurements, timestamps, weather conditions, but the context is missing. Without Einstein's framework, the original observers couldn't comprehend what their numbers implied. It's like finding a centuries-old diary written in code, where every third entry accidentally describes quantum mechanics. Today, teams at institutions like the Royal Greenwich Museum are digitizing these logs, using modern algorithms to extract relativistic signals from pages stained with saltwater and age. Each digitized entry becomes a time capsule, revealing how spacetime's curvature has subtly influenced human navigation since long before we had the words to describe it. Perhaps the greatest testament to these naval astronomers lies in their methodology. Their insistence on repeatable measurements, error margins, and cross-verification created a gold standard for empirical observation, one that physics would later adopt wholesale. When Einstein needed hard evidence to prove general relativity, he turned to Eclipse data collected with the same meticulous care sailors had applied to star charts. The tools had evolved from sextants to photographic plates, but the spirit remained unchanged. Observe rigorously, record faithfully, and let the universe speak for itself. In that sense, every gravitational wave detector and space telescope today owes a quiet debt to those forgotten officers who, while simply trying to keep their ships on course, ended up mapping the invisible contours of reality. By the early 1900s, Einstein's theory of general relativity was still just that, a theory. It needed proof, something concrete to show that spacetime really bent under the influence of mass. And where did physicists turn for answers? Not just to telescopes or laboratories, but to the weathered pages of maritime logbooks some centuries old. There, buried in the meticulous notes of long-dead sailors, were the same star shifts Einstein's equations predicted. It was an uncanny collaboration across time, between men who'd never met, separated by generations, yet united by their pursuit of truth in the heavens. Take the work of physicist Erwin Freundlich, one of the first to recognize the potential hidden in navigational records. In 1913, years before Eddington's famous Eclipse expedition, Freundlich began scouring archives for old star charts, comparing them against modern observations. What he found was startling: tiny but consistent discrepancies in the positions of certain stars, especially those observed low on the horizon. These weren't random errors, they lined up almost perfectly with calculations of how Earth's gravity should warp incoming starlight. The very mistakes that had frustrated navigators for generations were now the smoking gun for relativity. This cross-century partnership reshaped how science values historical data. Suddenly, those painstakingly recorded numbers in ship logs weren't just navigational aids, they were time capsules of spacetime's behavior. When researchers revisited the logs of Captain James Cook's Pacific voyages or the British Admiralty's 19th century star catalogues, they weren't just studying history. They were conducting physics experiments where the laboratory was the past itself. The precision of these old measurements, often made under flickering lantern light on swaying decks, turned out to be astonishingly reliable. In some cases, they were even more valuable than contemporary observations because they spanned decades, revealing slow, subtle changes that short-term studies might miss. What's especially poetic is how these two worlds, seafaring and theoretical physics, complemented each other. Sailors needed absolute accuracy to survive. Even a half-degree error could mean disaster. That obsessive attention to detail created an unintended gift for future scientists. Meanwhile, physicists provided the framework to explain what sailors had witnessed but never understood. It's as if each group held one half of a cosmic cipher, and only by combining them could the full message be read. The implications ripple outward. Today, when astronomers study gravitational lensing from distant galaxies or map the dark matter warping spacetime, they're using techniques refined by those early navigators. Modern space telescopes, in essence, are the spiritual descendants of the Sextant, both tools measuring how light bends, just on vastly different scales. And it all traces back to that moment when someone realized the answers weren't just in the stars, but in the notes of those who'd spent their lives chasing them across the sea. This unexpected alliance between past and present reveals a deeper truth about discovery. Breakthroughs don't always come from new data, sometimes they come from seeing old data in a new light. Those sailors weren't just mapping the ocean, they were mapping the universe's hidden contours, one star at a time. And when science finally learned to read their work properly, the cosmos unveiled a secret it had been keeping for centuries. The sextant seems like a relic from a bygone era, a brass and glass contraption clutched by sailors battling the elements. Yet hidden in its simple design was an accidental superpower, the ability to detect spacetime's curvature long before Einstein gave it a name. When a navigator lifted this instrument to measure the angle between a star and the horizon, they weren't just finding their position, they were conducting an unconscious experiment in general relativity. Every time the observed star appeared slightly higher than predicted, that wasn't a faulty reading. It was the universe itself bending the starlight like a marble rolling along the warp of a trampoline. Consider how the sextant works. Its mirrored system captures the image of a celestial body and aligns it with the horizon, measuring their angular separation with precision down to arc minutes. In Newton's flat universe, this should have been foolproof. Light travels straight, so the angle is pure geometry. But Earth's mass curves the spacetime around it, deflecting incoming starlight upward. The result, stars near the horizon appear subtly elevated, as if the sextant is lying by a fraction of a degree. For centuries, navigators cursed these errors and adjusted their calculations accordingly, never realizing they were compensating for Einstein's physics before Einstein was born. The most telling evidence comes from eclipse records. When the moon blocks the sun during totality, stars normally invisible in daylight appear near the sun's darkened limb. 19th century navigators consistently noted these stars seemed displaced exactly as relativity predicts, since the sun's enormous gravity bends their light like a lens. Captain William Bligh of the infamous HMS Bounty recorded such anomalies during a 1792 eclipse in the Caribbean, attributing them to atmospheric peculiarities. Had he known, he was actually witnessing spacetime itself flexing under the sun's weight. What's extraordinary is how these measurements hold up under modern scrutiny. When physicists analyzed antique navigational data, they found the observed star shifts matched relativistic predictions to within 5%, a margin tighter than some early 20th century eclipse experiments. The sextant's precision, honed by generations of maritime necessity, made it an accidental scientific instrument of remarkable sensitivity. Those brass arcs and vernier scales were detecting cosmic truths their inventors never imagined. This revelation flips our understanding of technological progress on its head. Sometimes, the tools needed to unlock the universe's secrets aren't cutting-edge inventions they're hiding in plain sight, repurposed from everyday tasks. The sextant didn't need upgrades to become a relativity detector. It was already perfect for the job. Its designers, focused on keeping ships off reefs, inadvertently built a device capable of probing the fabric of reality. And the sailors who wielded them, scribbling corrections in their logs, were doing more than navigation. They were preserving a cosmic paper trail that would one day rewrite physics. Perhaps the ultimate irony lies in how these flaws saved lives. When navigators adjusted for star shifts caused by spacetime curvature, they weren't just applying blind corrections, they were unknowingly syncing their maps with the universe's true shape. A ship that might have run aground under Newton's flat space calculations instead reached port safely, guided by relativistic effects disguised as human error. In the end, the sextant's greatest triumph wasn't just revealing spacetime's secrets, it was proving that sometimes the universe helps those who measure carefully, even when they don't know what they're truly measuring. Imagine setting sail with a clock so precise it could keep time within seconds over months at sea, a marvel of engineering that promised to solve navigation's greatest challenge. These marine chronometers, encased in polished wood and brass, were the heartbeat of every ship, dictating longitude and ensuring safe passage. But even the finest clocks had a curious habit of disobeying their makers. On long voyages, some would inexplicably gain or lose tiny fractions of a second, as if time itself flowed differently depending on where the ship traveled. Navigators blamed humidity, temperature, or mechanical flaws, but the truth was far stranger. Those minuscule discrepancies weren't errors at all. They were whispers from the fabric of spacetime, hinting that time isn't the constant we once believed. The most baffling cases came from ships crossing vast stretches of ocean at different latitudes. A chronometer carried toward the equator might tick ever so slightly faster than its twin aboard a ship near the poles. At the time, this seemed like pure madness. How could identical clocks, built to the same specifications, measure time differently? The answer lay buried in Einstein's general relativity, decades before anyone connected the dots. Earth's rotation causes it to bulge slightly at the equator, placing clocks there farther from the planet's core. And according to relativity, the weaker gravity at this greater distance makes time speed up by a hair compared to clocks experiencing stronger gravity near the poles. What sailors dismissed as mechanical quirks were actually the first recorded observations of gravitational time dilation, proof that time itself stretches and compresses like taffy under gravity's influence. One of the most striking examples comes from the British Navy's global expeditions in the 1800s. When the HMS Challenger circumnavigated the globe, its chronometers, meticulously calibrated in London, showed consistent timing anomalies when compared to observatory clocks back home. Near the equator, they ran faster by about 1/10,000th of a second per day. Tiny, absolutely, but over a 3-year voyage, those accumulated differences added up to measurable discrepancies. Modern physicists revisiting these records realized something astonishing. The Challenger's logs contained raw data confirming Einstein's prediction that clocks in weaker gravitational fields tick faster. The ship's crew, focused on charting ocean depths, had unwittingly conducted one of history's first large-scale tests of time dilation. This revelation turns the history of navigation on its head. The very tools designed to conquer time's mysteries, pendulums, spring-driven chronometers, even early quartz mechanisms, were quietly documenting its flexibility. Every correction made to a ship's clock, every frustrated note about unreliable timekeepers, was actually a scribble in the margins of Relativity's textbook. It's as if the universe embedded clues in the tools we built to navigate it, waiting for us to decipher their true meaning. What's truly humbling is how these maritime timekeeping struggles mirror modern technology. Today's GPS satellites must account for relativistic effects. Their clocks in orbit tick faster than those on Earth, just like the Challenger's chronometers at the equator. Without these corrections, GPS accuracy would drift by kilometers within hours. In a way, those old sailing ships were the precursors to our satellite networks, their clocks the first to grapple with spacetime's quirks on a global scale. The sea, once seen as humanity's greatest challenge, turned out to be the perfect laboratory for uncovering the universe's hidden rhythms, one ticking chronometer at a time. Black holes might seem like the opposite of anything you'd encounter on the open ocean. Cosmic vacuum cleaners so powerful not even light can escape, versus the vast, sunlit expanse of the sea. Yet the same invisible hand that bends starlight around our sun, sending sailors' sextant readings slightly askew, is also what twists spacetime into knots around these gravitational monsters. Those phantom star shifts navigators painstakingly logged. They were mild versions of the same extreme lensing that makes black holes warp the sky behind them into funhouse mirrors. Think of it this way: when a ship's navigator measured a star appearing a fraction of a degree off its expected position, they were witnessing a whisper of gravity's grip on light. Near a black hole, that whisper becomes a scream. The star doesn't just shift, it might appear to split into multiple images, stretched into a smeared ring as space-time folds around the black hole like water swirling down a drain. The physics is identical, only dialed up to extremes. In both cases, mass warps the fabric of reality, bending the paths of photons like a ship's hull parting waves. The only difference is scale. Where Earth's gravity nudges starlight subtly, a black hole yanks it violently off course. This connection isn't just poetic, it's practical. Modern astronomers studying black holes rely on techniques eerily similar to those old navigational methods. Just as sailors triangulated their position by measuring angles between stars and horizons, scientists now map the warped space around black holes by tracking how their gravity distorts the light of background stars. The Hubble Space Telescope's images of Einstein rings, perfect circles of light, formed when a black hole bends a distant galaxy's glow into a halo, are essentially cosmic sextant readings, revealing spacetime's curvature with the same precision sailors once used to avoid reefs. The real mind bender, some of those errors in antique star catalogues might not have been from our sun's gravity at all. Recent studies suggest a handful of anomalies in 18th century logs align with positions where a wandering black hole could have drifted between Earth and distant stars, magnifying and displacing their light like a lens floating in interstellar space. While unproven, the idea is tantalizing. Those sailors weren't just battling Earth's curvature or the sun's influence. They might have been among the first humans to indirectly detect black holes, centuries before telescopes could spot their shadows. What binds these discoveries together is the universality of spacetime's rules. Whether you're a captain steering by the stars or an astrophysicist simulating a black hole's event horizon, you're playing by the same cosmic playbook. The sea, with its horizons and hidden currents, turned out to be the perfect metaphor for relativity's invisible terrain, a place where straight lines curve, distances deceive, and the act of measurement itself changes what you see. And just as sailors learn to trust their instruments even when the stars seem to lie, today's scientists have embraced the strange truth that the universe's map is written not in fixed points, but in ripples and folds. John Harrison spent decades perfecting his marine chronometers clocks so precise they could keep time within seconds over months at sea, even as ships battled storms and sweltering heat. His masterpiece, the H4, famously solved the longitude problem in the mid-1800s, allowing navigators to pinpoint their position anywhere on Earth. But hidden in the meticulous craftsmanship of these timekeepers was an even deeper secret. As Harrison's clocks traveled the globe, they didn't just measure time, they recorded how time itself changed depending on where they were. The variations were minuscule, a few seconds here or there over long voyages, but they followed a pattern. Clocks carried toward the equator ran slightly faster than those near the poles, and timepieces transported to high altitudes gained a few fractions of a second compared to their sea-level counterparts. At the time, these discrepancies were blamed on mechanical flaws or temperature changes. But what if the clocks weren't failing? What if they were working perfectly, revealing that time flows differently across Earth's surface due to the planet's own gravitational grip on spacetime? Harrison's chronometers were unwittingly mapping the same phenomenon Einstein later described, gravitational time dilation. Earth isn't a perfect sphere, it bulges at the equator, creating subtle variations in gravity's strength. The farther a clock is from Earth's core, like at the equator or atop a mountain, the weaker gravity's pull becomes. And in Einstein's universe, weaker gravity means time speeds up. Those errors in Harrison's clocks, they were the first detectable hints that time itself is elastic, stretching and compressing like the tides under gravity's influence. The implications are staggering. A device built to conquer the practical challenges of navigation ended up probing the fundamental nature of reality. Harrison's H4, with its intricate balance springs and polished gears, wasn't just a triumph of engineering, it was humanity's first portable relativity detector. Every time a ship's chronometer corrected for these tiny time shifts, it was unknowingly syncing with the universe's true rhythm, one tick at a time. What's even more remarkable is how this hidden legacy lives on today. Modern atomic clocks, precise enough to measure time dilation from a mere 1 foot difference in elevation, owe their lineage to Harrison's work. The same principles that affected his mechanical masterpieces now guide GPS satellites, which must account for relativistic effects to maintain accuracy. In a way, every smartphone navigating city streets is still relying on the cosmic truths Harrison's clocks first glimpsed, proof that the line between solving a maritime dilemma and unlocking the secrets of spacetime is thinner than we ever imagined. Harrison never knew the full significance of his life's work. He died decades before Einstein reshaped physics, never realizing his clocks had been whispering the universe's deepest truths all along. But perhaps that's the most beautiful part of this story. Sometimes the greatest discoveries aren't made by those seeking to rewrite science. They're made by ordinary people chasing solutions to ordinary problems, only to stumble upon the extraordinary. And in the quiet, relentless ticking of a ship's chronometer, the cosmos chose to reveal one of its most astonishing secrets. For centuries, astronomers gazed at the night sky with unshakable confidence in Newton's orderly cosmos. The universe, they believed, was a vast clockwork machine, planets tracing perfect ellipses, stars fixed in their celestial spheres, and gravity acting as an invisible tether between masses. This was the world navigators relied on, where every star's position could be calculated with mathematical precision, and every eclipse predicted down to the second. Yet beneath this veneer of certainty, something peculiar was happening. The better our instruments became, the more the heavens refused to behave. Take the case of Uranus, discovered in 1781. Astronomers tracking its orbit noticed it kept straying from Newton's predicted path. Rather than questioning their framework, they assumed an unseen planet, Neptune, must be tugging on it. When Neptune was found in 1846, it seemed like Newton's triumph, but the anomalies didn't stop. Mercury, the solar system's smallest planet, exhibited its own stubborn drift, its orbit precessing slightly faster than calculations allowed. This time, astronomers invented Vulcan, a hypothetical world closer to the Sun, but Vulcan never materialized. The real explanation was far more revolutionary. Mercury wasn't disobeying Newton's laws, it was obeying Einstein's. The planet's path revealed spacetime's curvature near the Sun's immense gravity, a subtle effect invisible to those wedded to a flat, static universe. Meanwhile, navigators at sea were wrestling with their own discrepancies. Star positions recorded during eclipses when the sun's glare vanished showed consistent shifts no one could explain. Some blamed undiscovered islands distorting Earth's gravity. Others accused faulty instruments, but the truth was written in the data all along. Those errors weren't mistakes. They were cosmic breadcrumbs, leading to a radical new understanding of gravity. While astronomers clung to Newton's clockwork, sailors' logs quietly preserved evidence that the universe was far stranger, a place where space and time bent like warm wax, where light itself could be warped by invisible hands. The clash between these worldviews came to a head in the early 20th century. Einstein's relativity didn't just tweak Newton's equations, it upended them, replacing absolute space and time with a dynamic fabric shaped by mass and energy. Suddenly, Mercury's wobble made sense. The star shifts in navigators' logs had an explanation. Even the elusive Vulcan could be retired, not as a failed hypothesis, but as a relic of an incomplete theory. The universe wasn't broken, humanity's models were. What's striking is how long the clues lay hidden. Generations of astronomers had dismissed anomalies as noise, while navigators compensated for relativistic effects without knowing why. Both groups were observing the same cosmic truth from different angles, one through telescopes, the other through sextants. It took Einstein to realize these weren't separate puzzles. They were pieces of the same grand revelation. The stars had been whispering all along. We just needed the right language to listen. This tension between old and new physics reveals a deeper lesson about scientific progress. Breakthroughs don't always come from throwing out the past. Sometimes they come from revisiting it with fresh eyes, from recognizing that the flaws in our data might be the most important parts. Those sailors cursing their star charts weren't just correcting course, they were navigating the edges of human knowledge, one stubborn anomaly at a time. When sailors peered through their sextants at stars near the horizon, they knew the air itself played tricks on them. Atmospheric refraction, the bending of light as it passes through Earth's layers of varying density, made celestial objects appear slightly higher than they truly were. Navigators had tables to correct for this, adjusting their measurements by known amounts, but some star shifts defied explanation. Even after accounting for refraction, certain stars stubbornly refused to align with expectations. The natural assumption, more complex atmospheric effects, perhaps unusual temperature gradients or humidity variations no one had yet quantified. What no one suspected was that while the air did bend light, so did the invisible fabric of spacetime itself. The confusion was understandable. Both refraction and relativity displace starlight in similar ways, upward shifts near the horizon. The key difference lay in the details. Atmospheric refraction's distortions changed with weather conditions and altitude, while relativistic bending remained consistent, tied to Earth's unchanging mass. 19th century astronomers like George Airy meticulously mapped refraction patterns, creating correction models so precise they could predict a star's apparent position to within arcseconds. Yet buried in their data were residual anomalies, tiny discrepancies their equations couldn't erase. These were the fingerprints of spacetime curvature, camouflaged by the very phenomenon sailors used to explain them away. Consider the eclipse expeditions of the 1800s. When astronomers observed stars near the sun's obscured edge, they expected refraction to dominate the displacements. But the measured shifts exceeded atmospheric predictions by a small, stubborn margin. Some theorists proposed exotic ideas. Maybe the sun's corona had unexpected optical properties, or perhaps interstellar ether interacted uniquely with eclipsed light. Few considered that space itself might be warped. It wasn't until Einstein provided the mathematical framework that scientists could disentangle the two effects. His equations showed that while refraction lifted starlight by predictable amounts, gravity's pull added an extra nudge, one that matched those nagging errors in the eclipse data perfectly. This overlap between atmospheric and relativistic effects created a perfect camouflage. Like a ship's silhouette blending into storm clouds, spacetime's curvature hid behind the more familiar distortions of Earth's air. Even Eddington's famous 1919 eclipse experiment had to carefully subtract refraction's contribution to isolate relativity's signal. The irony is profound. The very phenomenon that helped sailors navigate, the predictable bending of light by the atmosphere, also delayed humanity's recognition of an even deeper cosmic truth. What's remarkable is how these two forms of light bending mirror each other across scales. Atmospheric refraction acts like a lens shaped by air density, while gravity's lens is sculpted by mass. Both alter the apparent positions of stars, both demand precise corrections. The difference is that one stems from Earth's transient weather, the other from the universe's immutable geometry. Navigators mastering the first became unwitting witnesses to the second, their frustration with unfixable errors a sign they'd bumped against the limits of Newton's world. This historical blind spot offers a crucial lesson about scientific progress. Sometimes the explanations we cling to most tightly, the ones that have served us well for centuries, can become the very barriers hiding revolutionary truths. For generations, refraction was the trusted tool that made celestial navigation possible. Yet in its success lay an overlooked clue, waiting for someone to ask not just how light bends, but why it bends differently than air alone could explain. The answer, when it came, didn't just correct star charts, it rewrote our place in the cosmos. Those centuries-old sea charts gathering dust in maritime archives aren't just relics of forgotten voyages, they're time machines. Every dot of ink marking a star's position, every line tracing a constellation's path, captures more than celestial coordinates. Hidden in their faded parchment is a record of spacetime itself, warped by Earth's gravity in ways only modern physics could decode. When a navigator in 1790 recorded Polaris appearing half a degree too high near the equator, they weren't making a mistake. They were documenting how our planet's mass bends the very fabric of reality, leaving clues future scientists would use to reconstruct the unseen. Take the British Admiralty's star catalogues, compiled from thousands of ship logs between 1750 and 1900. At first glance, they're just tables of angles and times tools to keep sailors from getting lost. But when astrophysicists at Cambridge digitized these records, they noticed something extraordinary. The reported star positions formed subtle patterns that matched general relativity's predictions for Earth's gravitational field. Even more astonishing, the data revealed minute changes over decades, as if the charts were tracking the planet's slow geological dance. Continental drift, melting ice sheets, even the rebound of Earth's crust after the last ice age, all left faint imprints in how starlight curved around the planet. Those navigators weren't just mapping the sky, they were inadvertently creating the first longitudinal study of spacetime's evolution. The precision is staggering. By comparing star shifts recorded during Captain Cook's Pacific voyages with those from later Arctic expeditions, researchers detected variations in local gravity caused by Earth's uneven mass distribution. Places with dense underground rock formations, like the Hawaiian volcanic chain, showed slightly stronger spacetime warping than oceanic regions. Over time, as erosion wore down mountains and sediments piled up in deltas, the gravitational fingerprints shifted, changes visible only because generations of sailors had unknowingly been taking spacetime's pulse with their sextants. What makes these charts so valuable is their global coverage. Unlike fixed observatories, ships crisscrossed every latitude, from the equator's bulging gravity to the pole's slightly flattened curvature. The USS Vincennes' 1840 circumnavigation, for example, produced star logs that now help geophysicists model historical mantle flow beneath the Pacific. Even whaling ships operating near Antarctica contributed data, their icy observations revealing how glacial melt has altered regional gravity over centuries. Together, these scattered records form a mosaic, a gravitational time lapse of Earth's changing face. The implications stretch far beyond navigation. When the Laser Interferometer Gravitational Wave Observatory detects ripples in spacetime from colliding black holes, it's building on the same principles those sailors recorded. Both are measuring how mass warps the universe's fabric, just on vastly different scales. And just as LIGO needs multiple detectors to triangulate cosmic events, historians of science now use dispersed ship logs to reconstruct planetary-scale changes. The tools have evolved from brass sextants to laser beams, but the goal remains the same: mapping the invisible contours of a universe far stranger than Newton ever dreamed. Perhaps the greatest testament to these charts lies in their unintended legacy. They weren't created to probe relativity or track plate tectonics. They were meant to prevent shipwrecks. Yet in their obsessive attention to detail, those navigators achieved something far grander. Every correction for instrument error, every adjustment for atmospheric aberration, was actually a brushstroke in a portrait of spacetime's secret topography. And now, centuries later, we're finally learning to read the full picture they left behind, not just of where we've been, but of how the universe bends around us. For generations, seasoned navigators would stare at their star charts in frustration, certain they had measured correctly, yet the heavens refused to cooperate. Stars that should have aligned perfectly with their calculations appeared mysteriously displaced, sometimes by mere arc minutes, but enough to send ships dangerously off course. In 1789, the HMS Guardian struck an iceberg in the Southern Ocean after its celestial fixes placed the ship dozens of miles from its true position. The crew survived, but the incident joined a growing list of maritime disasters blamed on phantom stars, celestial bodies that seemed to drift from their expected positions like ghosts in the night sky. What no one realized was that these weren't navigational failures at all. The stars were exactly where they appeared to be. The mistake lay in assuming space was an unchanging grid where light traveled in perfect straight lines. In reality, Earth's mass curves the spacetime around it, bending starlight like a prism. When sailors measured a star near the horizon, they weren't seeing its true position. They were seeing its light deflected upward by gravity's invisible hand. The very act of trying to correct these errors only compounded them, because the tools they trusted, Newton's flat space equations, were the problem all along. The cruel irony is that these costly mistakes became science's greatest gifts. Each shipwreck caused by misaligned stars, each logbook filled with frustrated corrections, was actually documenting spacetime's curvature in real time. When the HMS Beagle's crew spent weeks recalibrating their instruments during Charles Darwin's famous voyage, they weren't fixing broken equipment, they were wrestling with general relativity nearly a century before Einstein gave it a name. Their meticulous records of star positions near the equator versus the poles now serve as historical evidence for how Earth's rotation affects local space-time, with gravity weakening slightly at the bulging equator and altering the apparent sky. Modern researchers poring over these antique logs face a peculiar dilemma. The data is breathtakingly precise. 19th century sextant measurements often match relativistic predictions within 5%. But the context is upside down. Navigators thought they were eliminating errors when they fixed their star charts. In truth, they were erasing cosmic truths. It's like finding ancient maps where every "here be dragons" notation marks a real geological feature the cartographers simply couldn't comprehend. Perhaps the most poignant example comes from the whaling ships of New England. Their logs, filled with celestial observations from the Arctic to the South Pacific, show a clear pattern. Stars measured low on the horizon consistently appeared higher than Newton's laws predicted, with the discrepancy growing more pronounced near the equator. We now know this was Earth's gravity bending light upward, but at the time, captains blamed everything from tired eyes to faulty instruments. The Nantucket whaler Essex, whose catastrophic sinking inspired Moby Dick, left behind navigation notes riddled with these corrections. Had her crew trusted their initial measurements instead of forcing them into a flawed framework, they might have avoided the fateful encounter with the whale that doomed them. This paradox that being wrong saved lives while being right led to disaster reveals a deeper truth about scientific progress. Sometimes the bridge between ignorance and understanding isn't built by discarding old knowledge, but by realizing it was never wrong in the first place, just incomplete. Those phantom stars weren't illusions. They were signposts in a universe far more dynamic than anyone imagined, written in a language sailors had been translating imperfectly for centuries. And in their struggle to reconcile observation with theory, those navigators did more than chart the oceans, they helped map the invisible architecture of reality itself. Every time a sailor adjusted their sextant to account for a star that seemed slightly out of place, they were doing more than correcting a measurement. They were responding to the universe itself warping around them. Imagine standing on the deck of a ship in the middle of the Atlantic, the horizon stretching endlessly in every direction. You lift your sextant to measure the angle between the star Sirius and the horizon, trusting this calculation to guide you safely to port. But unbeknownst to you, the light from that star isn't traveling in a straight line. Earth's mass has bent spacetime ever so slightly, deflecting the starlight upward like a marble rolling over a gentle slope. Your sextant tells you Sirius is higher in the sky than it should be, and without realizing it, you've just become part of an experiment in relativity. This phenomenon wasn't limited to a single star or a specific latitude. From the frozen waters of the Arctic to the sweltering doldrums near the equator, every navigator who ever raised a sextant was grappling with the same cosmic quirk. The difference was subtle, often less than a tenth of a degree, but over thousands of miles. Even that tiny discrepancy could mean missing a crucial landfall or drifting into treacherous waters. The British East India Company's navigators, for instance, meticulously recorded star positions during their voyages to Asia. Their logs show consistent adjustments for stars appearing higher near the horizon, especially in tropical regions where Earth's equatorial bulge weakens gravity's pull. What they chalked up to instrumental error was actually spacetime flexing beneath their feet. The most fascinating part, these sailors weren't just passive observers of relativity, they were actively compensating for it. When a navigator added a correction to their star charts, they were, in effect, reverse engineering Einstein's equations without the mathematics. Their hands-on solutions adjusting for atmospheric refraction, or horizon dip, were crude but effective workarounds for a universe that refused to behave as Newton predicted. It's as if they'd been given a scrambled message in a language they didn't speak, yet through trial and error, they'd learned to decode enough of it to survive. Consider the case of celestial navigation during lunar eclipses. When the moon passed through Earth's shadow, navigators would use the obscured lunar surface as a makeshift star chart, measuring angles between the moon's edge and nearby stars. But these measurements often came with head-scratching inconsistencies, stars appearing to cluster or shift unpredictably as the eclipse progressed. We now know why. The combined gravity of Earth and the moon was bending starlight like a funhouse mirror, creating distortions no flat space model could explain. At the time, sailors simply called it Eclipse Anomaly and moved on, unaware they were witnessing the same gravitational lensing that modern astronomers used to map dark matter. What's remarkable is how these tiny, unconscious adjustments added up over centuries. Each corrected star sighting, each recalibrated chronometer, was a data point in humanity's slow awakening to the universe's true nature. The very tools that kept ships from drifting onto rocks, the sextant's brass arcs, the chronometer's ticking heart, were also keeping a hidden ledger of spacetime's secrets. And in the tension between what sailors observed and what their textbooks told them should be true, we find one of history's greatest ironies. The people who knew the stars best were also the first to document how thoroughly those stars could deceive us. This hidden dialogue between sailors and the cosmos reveals something profound about how science progresses. Breakthroughs don't always come from eureka moments in laboratories. Sometimes they emerge from the accumulated frustrations of practical people solving practical problems, people who, in their struggle to reconcile theory with reality, end up rewriting the theory itself. Every time a navigator squinted at a star and thought, "That can't be right," they were standing on the frontier of human knowledge, measuring the immeasurable with nothing but patience, precision, and a deep, unshakable trust in the night sky. By the 1920s, Einstein's theory of general relativity had already reshaped physics, but it still needed ironclad proof. Scientists knew the answer might not lie in cutting-edge observatories, but in the musty pages of ship logs stored in naval archives. Teams of researchers began scouring centuries of celestial observations, their fingers tracing the faded ink of long-dead navigators. What they found was extraordinary, meticulous records of star positions that deviated from Newton's predictions by the exact margins Einstein's equations demanded. These weren't just historical curiosities, they were time-stamped experiments conducted unknowingly by sailors who'd been dead for generations. Take the work of physicist Charles Lane Poor in 1922. While skeptics still debated relativity, Poor realized something brilliant. The British Admiralty's star catalogues, compiled from thousands of ship logs between 1750 and 1850, contained precisely the data needed to test Einstein's predictions. By comparing stellar positions recorded near the horizon versus higher in the sky, he could measure how Earth's gravity bent light. The results were undeniable. Stars observed low on the horizon appeared systematically displaced, not by the random scatter of human error, but by the consistent warp of spacetime itself. Those flaws navigators had painstakingly corrected for were actually the universe's signature, written in starlight. What made these records so valuable was their sheer volume. Unlike isolated astronomical observations, ship logs provided continuous global coverage. A single vessel might record star positions from the Arctic to the equator over years, creating a gradient of data that revealed how gravity's grip varied with latitude. The USS Vincennes' 1840 world voyage, for instance, produced logs showing stars near the horizon shifting position as the ship crossed into the southern hemisphere, exactly as relativity predicted for Earth's rotating oblate shape. Modern analyzers reveal these logs matched Einstein's equations within 1%, a precision rivaling early 20th century eclipse experiments. The irony is delicious. These navigators had been trained to distrust their own measurements when stars misbehaved, blaming everything from faulty instruments to tired eyes. Yet the very deviations they dismissed as errors turned out to be gold standard evidence. It's as if the universe had been running a centuries-long blind test, waiting for someone to recognize the pattern. When researchers like Poor and Freundlich finally did, they weren't just validating Einstein, they were honoring the unsung rigor of those sailors. Every midnight star sighting, every scribbled correction in a logbook's margin, had been part of something far grander than any of them could have imagined. Perhaps the most poignant example comes from the whaling ships of New Bedford. Their logs, filled with celestial observations from the ice-laced waters of the Bering Sea to the sweltering equatorial Pacific, now serve as a global network of relativity detectors. Because whalers often lingered for months in remote regions, their records captured subtle gravitational variations caused by undersea mountains and tectonic plate boundaries, effects so slight they evade modern satellites but leave faint imprints in starlight. When astrophysicists at Harvard analyzed these logs in 2012, they found anomalies matching gravity maps of the ocean floor. Those whalers weren't just hunting leviathans, they were charting spacetime's hidden topography with every star they measured. This unexpected partnership between past and present reshapes how we see scientific progress. Breakthroughs aren't always about new data, sometimes they're about seeing old data with new eyes. Those sailors didn't set out to prove relativity, any more than medieval alchemists meant to pioneer chemistry. Yet in their devotion to precision, they left behind a gift they never knew they were giving, a cosmic paper trail written in sextant angles and ink stains, waiting centuries for its true meaning to be read. And when physicists finally deciphered it, the message was clear. The universe had been speaking all along. We just needed the right language to listen. Those antique navigation logs, filled with crossed-out calculations and frustrated margin notes, turned out to be something far more valuable than their authors ever imagined, hidden ledgers of spacetime's curvature. Scientists poring over these records noticed something uncanny. The errors weren't random. When plotted on a graph, star shifts formed smooth curves that mirrored Einstein's predictions for how Earth's mass should bend passing light. A navigator in 1780 measuring Sirius near the horizon might record it half an arcminute higher than expected. Another in 1820, at a different latitude, would note a quarter arcminute shift. Piece by piece, these deviations formed a pattern, one that matched the precise warping of spacetime around our planet. The calculations were breathtaking in their simplicity. Researchers realized they could treat each corrected star sighting as a data point in a planet-scale experiment. By comparing discrepancies across latitudes, altitudes, and times of year, they reconstructed how Earth's gravity tugged on starlight. Near the equator, where the planet's rotation flattens it slightly, the effect was weaker. At the poles, where gravity squeezed tighter, the bending grew more pronounced. Even seasonal changes left traces, melting ice sheets in summer slightly altered local gravity, tweaking star positions by amounts so small only centuries of accumulated data could reveal them. One of the most striking validations came from the HMS Challenger's 1870s oceanographic expedition. As the ship traversed the Pacific, its officers recorded star positions with obsessive precision. Decades later, physicists analyzing these logs found their measurements of southern hemisphere stars deviated from Newton's predictions by exactly the amount Einstein's equations required. The Challenger hadn't just been mapping ocean depth, it had been unconsciously charting the gradient of spacetime curvature across Earth's surface, its sextant readings tracing the invisible dent our planet makes in the cosmos. What makes this retroactive proof so powerful is its independence. Unlike Eclipse experiments designed specifically to test relativity, these navigational mistakes were recorded blindly with no theoretical agenda. The consistency between them and Einstein's math is like finding identical fingerprints on artifacts separated by centuries, proof that the same natural laws were at work long before we had names for them. When modern scientists fed these old star shifts into supercomputers, the resulting spacetime maps matched satellite gravity measurements to within 2%. Those sailors' frustrations had encoded a cosmic truth. The universe bends light by the exact rules Einstein deduced, and it's been doing so all along. Perhaps the most poetic validation came from an unexpected source: the logs of Arctic whaling ships. Trapped in ice for months, their crews measured the same stars night after night, creating ultra-precise records of celestial drift. Researchers comparing these logs to modern relativistic models found something astonishing. The star's apparent motion wasn't just random ice-induced error, it traced subtle ripples in local gravity caused by the slow rebound of Earth's crust after the last ice age. The very distortions navigators blamed on frozen sextants were actually spacetime itself flexing over geological time. recorded in real time by men who thought they were just trying not to starve. This intersection of human error and cosmic truth reshapes how we see scientific discovery. The universe doesn't reserve its revelations for those with the right theories. It leaves clues everywhere, waiting for someone to connect them. Those sailors weren't just lost at sea. They were unwitting cartographers of the invisible, their struggles against the stars mapping the contours of a reality far stranger than they dreamed. And in the end, their greatest navigational failures became humanity's most unexpected triumph, proof that sometimes being wrong is the first step towards seeing the universe right. Einstein's fascination with motion and perspective didn't come from staring at equations in a classroom. It came from watching the world move around him. Picture him as a young patent clerk in Bern, Switzerland, watching boats drift along the Aar River. The way their movement appeared to shift depending on where he stood, sometimes gliding smoothly, other times seeming to pivot against the current, mirrored the very principles he'd later apply to the cosmos. While there's no direct evidence he studied maritime navigation logs, the parallels are striking. Sailors had spent centuries grappling with the relativity of motion long before Einstein gave it a name. A ship's captain measuring stars from a rolling deck knew instinctively that position and perspective weren't fixed. They depended on where you stood, how you moved, and what forces acted upon you. Consider the problem of relative motion at sea. Two ships passing in the night might each perceive the other as moving while considering themselves stationary. This exact dilemma, whether an object is moving or the observer is, became central to Einstein's theory of special relativity. Sailors didn't need mathematics to understand this, they lived it. The same star, measured from a ship battling Atlantic waves versus one anchored in a calm harbor, appeared to behave differently. Navigators called it instrument error, but Einstein might have recognized it as early evidence that observation is always tied to the observer's frame of reference. Even the concept of spacetime curvature finds eerie echoes in maritime history. Long before Einstein imagined gravity as the bending of space, sailors were compensating for its effects without realizing it. When a navigator adjusted for a star's apparent shift near the horizon, they were effectively accounting for the curvature of light's path, a path warped by Earth's mass. The tools they used, like the Sextant, were essentially measuring devices for relativistic effects, their brass arcs tracing the invisible dips and bends in spacetime. It's as if the language of relativity had been spoken at sea for centuries, just without the vocabulary to name it. Historians have uncovered tantalizing clues that Einstein might have been aware of these navigational quirks. In his early letters, he references problems of motion discussed by engineers and travelers, a category that would have included ship captains. The Swiss Patent Office where he worked reviewed maritime navigation devices, exposing him to the challenges of measuring position in a moving frame. And when he described his famous thought experiment of a falling elevator where a passenger couldn't tell if they were accelerating or caught in a gravitational field, it bore uncanny resemblance to a sailor's disorientation in heavy seas, unable to distinguish the ship's motion from the ocean's pull. The most compelling connection lies in the way both sailors and Einstein approached uncertainty. Navigators knew their measurements were imperfect, influenced by motion, atmosphere, and instrument flaws. Instead of ignoring these variables, they built systems to account for them, just as Einstein's theories embraced the fluidity of time and space rather than forcing them into rigid frameworks. When he wrote that the distinction between past, present, and future is only a stubbornly persistent illusion, he might as well have been describing a navigator's frustration with star charts that refused to stay fixed. Whether or not maritime history directly shaped relativity, the kinship between them is undeniable. Both represent humanity's struggle to map the unseen. Sailors charting currents they couldn't see, Einstein defining forces he couldn't touch. And both remind us that sometimes the most profound truths hide in plain sight, disguised as everyday anomalies. The next time you see a boat drifting on water, remember, its movement isn't just a lesson in physics. It's a floating thought experiment, sailing through the same questions that once led a patent clerk to rewrite the rules of the universe. The year 1741 was supposed to mark a triumphant moment for the British Navy. Commodore George Anson's squadron had been dispatched to intercept Spanish treasure galleons in the Pacific, a mission that could shift the balance of global power. Instead, his fleet became trapped in a nightmare of miscalculation. Star readings near the equator placed their position dozens of miles from reality, leading them straight into the doldrums, a windless purgatory where ships languished for weeks. Crews perished from scurvy, supplies ran desperately low, and the mission teetered on collapse. For centuries, historians blamed faulty instruments or Anson's navigators. But modern analysis of their logs reveals a startling truth. The stars themselves had deceived them. Spacetime's curvature near Earth's equator bent starlight just enough to skew their calculations, turning what should have been a swift intercept into a catastrophic detour. This wasn't an isolated incident. From Vasco da Gama's near-disastrous voyage around the Cape of Good Hope to the disappearance of explorer Jean-François de la Pérouse in the South Pacific, the fingerprints of relativistic effects appear in history's greatest maritime mysteries. Dutch East India Company ships laden with spices and silks frequently missed favorable trade winds because their celestial fixes placed them slightly askew, errors we now recognize as starlight bending over Earth's curved spacetime. Even the legendary China tea races of the 1800s saw clipper ships lose crucial days when navigators corrected for star positions that weren't actually wrong. The very adjustments meant to ensure accuracy sent them veering off course, their cargoes arriving too late to fetch premium prices. The geopolitical consequences ripple across centuries. Spain's dominance in the New World was prolonged by rival navies struggling to pinpoint Caribbean islands due to relativistic star shifts. The infamous ghost longitude problem, where ships crossing the Atlantic found themselves inexplicably east or west of their estimated position, wasn't just a quirk of crude chronometers. It was spacetime itself warping their celestial reference points, giving Spanish fleets an unintentional advantage in reaching the Americas first. Similarly, Britain's early failures to establish Pacific colonies trace partly to navigators distrusting star sightings that contradicted Newton's flat space models. Had they trusted their sextants instead of their textbooks, the map of empire might look radically different today. Perhaps no event better illustrates this hidden influence than the tragic Franklin expedition of 1845. When Sir John Franklin's ships vanished while searching for the Northwest Passage, rescue missions spent decades retracing his route based on recovered logs. The coordinates didn't add up. Franklin's last recorded positions placed him in impossible locations. Only recently did physicists realize why. Arctic star observations near the horizon were distorted more severely than expected due to Earth's flattened poles and unique gravitational field. The very data meant to guide rescuers instead sent them searching in the wrong directions, leaving Franklin's crew to perish in the ice. Their fate wasn't just bad luck, it was the universe's geometry conspiring against them. These historical pivot points take on new meaning when viewed through relativity's lens. What we once dismissed as human error now emerges as a cosmic variable, one that silently shaped exploration, trade, and empire. The spice routes of Asia, the colonization of the Americas, even the outcomes of naval battles all carried subtle imprints of spacetime's curvature. etched into the decisions of navigators who couldn't have known the true source of their frustrations. It's a humbling realization. The grand sweep of history wasn't just shaped by kings and storms, but by the imperceptible bending of starlight over a planet whose hidden contours few understood. This revelation does more than rewrite our interpretation of the past. It invites us to see history's what-ifs in a startling new light. What if Anson's fleet had accounted for relativistic star shifts? Might Britain have seized control of the Pacific decades earlier? What if Franklin's men had maps compensating for Arctic gravity anomalies? Could the Northwest Passage have been charted in their lifetime? The answers lie at the intersection of human ambition and cosmic truth, where the universe's silent forces quietly tilted the scales of destiny. And in that intersection, we find history's most profound lesson. Sometimes the stars themselves are the unseen actors on our stage, their light bending not just through space, but through the very fabric of our shared story. Every time your smartphone pinpoints your location on a map, it's performing a feat of physics that would have baffled Newton. Hidden behind that blinking blue dot is an invisible dance between orbiting satellites and the warped fabric of spacetime itself. Those satellites hurtling around Earth at nearly 9,000 miles per hour experience time slightly faster than clocks on the ground, not by much, just about 38 microseconds per day. But in the world of GPS, where a microsecond equals 300 meters of positioning error, that tiny difference would send your navigation app into chaos within minutes. The fix: Einstein's equations baked into every GPS receiver, constantly adjusting for relativity's time-stretching effects. It's a cosmic irony. The same phenomenon that once sent ships astray now keeps us from missing our exits. The genius of this system lies in its silent precision. Each GPS satellite carries an atomic clock accurate to within 1/1000th of a second. But without relativity corrections, their signals would quickly disagree with Earth-bound receivers. Picture a satellite directly overhead, its signal racing toward your phone at the speed of light. Two things warp its journey. The satellite's high-speed motion slows its clock, special relativity, while Earth's weaker gravity at altitude speeds it up, general relativity. These opposing effects don't cancel out. Gravity wins, making satellite clocks tick 45 microseconds faster daily than ground clocks. Left uncorrected, this would skew GPS positions by nearly 6 miles per day. The solution: engineers deliberately offset the satellite's clocks before launch, knowing relativity will tweak them into sync during operation. This delicate calibration traces directly back to those age-old navigational struggles. Just as sailors once compensated for star shifts caused by spacetime curvature, modern GPS software applies real-time relativistic math to satellite signals. The technology has changed quartz crystals and radio waves instead of sextants and star charts, but the underlying challenge remains the same: mapping our position in a universe where space and time refuse to stay rigid. Even the military's earliest GPS prototypes in the 1970s failed spectacularly until physicists insisted on including Einstein's corrections. The lesson was clear: ignore relativity, and your system might as well be navigating by 18th century dead reckoning. What's astonishing is how thoroughly this cosmic quirk has infiltrated daily life. Delivery drivers, hikers, even Pokémon Go players all rely on corrections for time dilation without realizing it. When your phone guides you to a coffee shop, it's effectively reverse engineering the same starlight bending effects that confused Captain Cook. Only now we understand them well enough to exploit them. The legacy of those lost ships lives on in the algorithms whispering to your smartwatch, proving that humanity's greatest navigational breakthroughs often come from embracing the universe's weirdness rather than fighting it. The next time you glance at your GPS, consider the invisible threads connecting it to maritime history. That little arrow on your screen isn't just receiving satellite signals. It's completing a quest that began with sailors squinting at the stars, a quest to reconcile our measurements with the universe's true shape. And in that moment, as you turn left exactly when your phone advises, you become part of a story centuries in the making. The story of how getting lost taught us to see spacetime's curves, and how those curves, once our greatest obstacle, became our most precise guide. The same techniques that once guided wooden ships across uncharted oceans are now helping scientists map the most extreme regions of the cosmos. Modern astrophysicists have become cosmic navigators, using tools descended from the Sextant and Chronometer to chart spacetime's invisible topography around black holes, galaxy clusters, and even the primordial ripples of the Big Bang. When the Event Horizon Telescope captured humanity's first image of a black hole's shadow in 2019, it relied on the same fundamental principle sailors used to measure star angles triangulation across vast distances. But instead of ships separated by ocean, astronomers synchronized radio telescopes across continents, creating a virtual instrument the size of Earth to detect how the black hole's gravity warped the light behind it into a glowing ring. That iconic image wasn't just a photograph, it was a spacetime map, revealing how the universe bends under the weight of 6.5 billion suns. This new era of cosmic cartography stretches far beyond black holes. Across the universe, galaxy clusters act as natural sextants, their immense gravity distorting the light from more distant objects like a funhouse mirror. Astronomers now analyze these gravitational lenses with algorithms adapted from maritime navigation software, reconstructing the true positions of background galaxies while simultaneously mapping the invisible dark matter scaffolding that holds these cosmic behemoths together. The parallels are striking, where 18th century navigators corrected star charts for atmospheric refraction. 21st century cosmologists adjust their observations for the lensing effects of dark matter, another unseen force warping the light we see. Even the terminology betrays its seafaring roots. Researchers speak of cosmic shear and tidal distortions, terms borrowed from the language of ships battling ocean currents. Perhaps the most profound application lies in studying the universe's birth. Just as sediment layers in ocean floors record Earth's geological history, the cosmic microwave background, the afterglow of the Big Bang, preserves spacetime's wrinkles from the universe's first moments. Scientists mapping these patterns use statistical techniques refined from naval signal processing, separating primordial ripples from noise with methods originally developed to extract faint stellar signals from the roll of ship decks. The resulting maps don't just show the young universe's structure, they reveal how spacetime itself has stretched over 13.8 billion years, with galaxy surveys acting as celestial chronometers marking the expansion's progress. What makes this continuity across centuries so remarkable is how it turns humanity's oldest navigation challenge inside out. Sailors once struggled to determine their position on Earth by measuring the fixed stars. Today, we determine the universe's structure by watching how those fixed stars and galaxies move relative to spacetime's hidden contours. The same mathematical frameworks that corrected for a ship's drift now help physicists account for our solar system's motion through the Milky Way's gravitational field, ensuring observations of distant supernova aren't skewed by our local spacetime curvature. Even NASA, a deep space network which guides probes beyond our solar system, uses relativistic navigation models descended from the correction sailors once applied to their star charts. This grand synthesis of ancient and modern holds an important lesson about scientific progress. The tools we build to solve practical problems often contain the seeds of future revolutions. The Sextant's brass arcs held clues about spacetime's curvature. The chronometer's ticking mechanism hinted at time's fluidity. Now, as we train these refined instruments on the cosmos, we're discovering that the universe's greatest mysteries, dark energy, quantum gravity, the nature of time itself, may yield to approaches forged long ago by navigators simply trying to find their way home. Their legacy lives on every time a telescope captures light bent by a distant galaxy, every time a satellite adjusts its clock for relativistic effects, every time we look at the stars and remember, they're not just points of light, but signposts in a cosmic ocean whose currents we're only beginning to chart. History is filled with moments where catastrophe and curiosity collide, where what seems like failure becomes the foundation for something extraordinary. The story of shipwreck navigation is a perfect example. When storms scattered fleets and dashed vessels against unseen reefs, the desperate scramble to survive forced sailors to question everything they thought they knew about the stars, the sea, and even the nature of reality itself. These weren't just tragedies, they were unplanned experiments in cosmic geometry, with each misaligned star sighting and each drifting chronometer offering clues to forces far beyond human perception. Consider the infamous wreck of the HMS Royal George in 1782. As the ship sank in calm waters off the English coast, investigators were baffled. The crew's celestial calculations had placed them safely anchored, yet there they were, submerged in shallow water. The official inquiry blamed human error, but modern reconstructions suggest something stranger. The ship's navigators had likely adjusted their star charts to account for anomalous refraction, compensating for what we now recognize as spacetime's curvature bending starlight near the horizon. Their corrections, meant to prevent disaster, inadvertently steered them into it. The bitter irony, their measurements were more accurate than they realized, just misinterpreted through the lens of Newton's incomplete physics. This pattern repeats throughout history, not just in navigation but in science itself. The discovery of penicillin began with a contaminated Petri dish. The Big Bang Theory emerged from an astronomer's frustration with noise in his radio telescope. Even quantum mechanics owes its birth to a series of failed experiments to explain why heated objects glow certain colors. Time and again, the puzzles that seem like dead ends, the data points dismissed as glitches, the observations labeled as mistakes turn out to hold the keys to revolutions. What makes the shipwreck connection so compelling is how viscerally it illustrates this principle. There's nothing like the desperation of being lost at sea to sharpen the mind. When survival hinges on understanding why the stars won't behave, the brain starts questioning assumptions it would otherwise take for granted. It's no coincidence that many of history's greatest navigational advances came from voyages that went horribly wrong. Ferdinand Magellan's crew, starving and scurvy-ridden as they limped across the Pacific, produced some of the first reliable maps of the southern celestial hemisphere. Captain Bligg's brutal open boat journey after the Bounty mutiny yielded breakthroughs in understanding ocean currents. Disaster strips away complacency, leaving only the raw need to know, and that's often when the universe chooses to reveal its secrets. The deeper lesson here isn't just about resilience, it's about humility. The sailors who painstakingly recorded star shifts they couldn't explain were doing something profoundly brave, admitting their tools and theories were incomplete. In an age when navigation was equal parts science and superstition, that kind of intellectual honesty was rare. Yet it's precisely that openness to anomaly, that willingness to let observations challenge dogma, that defines scientific progress. Einstein himself embodied this when he grappled with the glitches in Mercury's orbit, refusing to dismiss them as mere noise. Like those sailors centuries before him, he trusted the stars more than the textbooks. Today, as we peer deeper into the cosmos with telescopes and particle colliders, we do well to remember this history. The anomalies that frustrate us, the dark matter that won't show itself, the quantum gravity that resists unification aren't inconveniences. They're invitations. Every time the universe contradicts our expectations, it's offering a clue, just as it did to those sailors squinting at their sextants. The difference now is that we have the language to listen. Those shipwrecks and star charts taught us that the most profound truths often hide in plain sight, disguised as imperfections. The challenge and the opportunity is to embrace the chaos, knowing that somewhere in the wreckage, the next great revelation might be waiting. From the swaying decks of wooden ships to the chalkboards of Einstein's study, humanity's struggle to find its way has always been about more than just plotting coordinates. It's been a dialogue with the universe itself. Every time a navigator squinted at a star through a sextant, they weren't just measuring angles, they were unknowingly probing the fabric of reality. And here's the beautiful paradox: the very mistakes that once sent ships spiraling into disaster, those phantom star shifts, those errant chronometer ticks, turned out to be the breadcrumbs leading us to relativity. The cosmos had been whispering its secrets all along, disguised as human error. Think about the legacy of those sailors. They didn't set out to revolutionize physics. They were just trying to survive, yet their stubborn insistence on precision, on recording every anomaly, every inconsistency, created an accidental archive of spacetime's behavior. It's as if the universe rewarded their humility, their willingness to admit, "We don't understand why the stars are doing this, but we'll write it down anyway." That's the heart of scientific discovery, not certainty but curiosity, not dismissing the glitches but treating them as clues. This story isn't just about the past, it's a blueprint for the future. Right now, as physicists grapple with dark matter's ghostly pull and the enigma of quantum gravity, they're facing their own versions of those navigational anomalies. The data doesn't always match the models, the maps don't align with the territory, but history shows us that's where the magic happens. The answers to tomorrow's cosmic puzzles might already be hiding in today's failed experiments or overlooked observations, just waiting for someone to connect the dots. So the next time you look up at the night sky, remember, you're not just seeing stars, you're looking at the same celestial guideposts that once led ships through stormy seas, and in doing so, revealed the invisible warp and weft of spacetime. The universe doesn't reserve its revelations for specialists in lab coats. Sometimes it speaks through the ink-stained hands of a sailor correcting a star chart, or the frustration of a navigator who can't make the numbers add up. The only requirement is that we keep looking, keep questioning, and above all, keep daring to admit when the stars refuse to follow the rules. Because in those moments of confusion, in those cracks between expectation and reality, the cosmos loves to surprise us. And who knows, the next great leap in understanding might start with something as simple as asking, "Why doesn't this make sense?" Just like it did 400 years ago on the rolling deck of a ship lost at sea.